Let's get this finished. So this is Lisa. She is not what I would call the most gifted in intelligence of our dogs, but she is trying to find out where the sun was born. So what I'm going to talk about here, this was the last challenge that Mike gave me, was to talk about where the sun might have formed. So I'm going to run through a whole lot of stuff that I don't work on, but drawing from the literature and liberally. Talk about the age of the sun, chemical composition, some things we covered before. And actually, Kathy dealt with some of this yesterday as well. Talk about the planetary system, its likely natal environment. There have been a number of searches to try and find solar siblings. I'll talk a bit about that. And then migration. Did it need to happen? And as Kathy said, the primary reference for this is a nice review article by Fred Adams, which I have leaned on heavily and liberally throughout. So the sun is the only star where we know the age to better than three significant figures. And that's basically because it's the only star where you can get a chunk of the material that it's formed from and stick it in a laboratory and measure radioactive ages. So the material comes from carbonation chondrites. And I guess one thing I should say is that when we talk about the age of the sun, we're really talking about the age of, or the time back to the first formation of solid material within the protostellar disk, the solar nebula. So carbonaceous chondrites are the meteorite that seems to be the most primitive. They include refractory materials, calcium aluminum inclusions. Actually, I guess they're calcium aluminum inclusions for our colleagues, cousins. And it's radiometric dating of those inclusions that's provided the age estimate of the oldest solids in the solar system. So there are three sets of reactions that are used to do this dating. Rubidium to strontium with a half-life of 49 billion years, uranium to lead, uranium-238 to lead-206, and uranium-235 to lead-207, with lifetimes of 4.5 billion years and 704 million years. And those three isotope ratios then have been used to estimate ages for this material. The original, or one of the earliest estimates, was Jerry Wasserberger, who came up with an age of, what does it say there, 4.56 billion years, based on strontium and rubidium ratios. Then the slope of that relation for these 6 different nodules gives the age of the age of the material. And then more recent measurements looking at the lead ratios come up with ages of 4.567.4 plus or minus 500,000 years. And there are some papers in the literature that point out that this could be uncertain by a few million years, since the uranium-238 and the uranium-235 ratio isn't well defined. But from an astronomical perspective, we'll take it. So that's a baseline measurement for the age of the solar system. The interesting thing is that helioseismology actually gives an estimate that's in agreement with that, and surprisingly accurate, perhaps. So in helioseismology, you're measuring the pulsational frequency of the sun. Astroseismology, you're looking at other stars. The pulsations depend on the sound speed within the core and within the envelope. And the sound speed depends upon the molecular weight. So within the core, the main factor for the molecular weight is the transition from hydrogen to helium. So that's where you get the age. As you transfer hydrogen, as hydrogen transforms into helium, then you increase the molecular weight of the core. You have to allow for the convective envelope. In the convective envelope, you have heavy metals. And that's where the solar composition comes in, because oxygen is the most dominant, is the highest abundance heavy element. So the most recent estimate that I've come across by Hudik and Goch comes up with an age of 4.60 plus or minus 0.4 gigayears. So 1% accuracy, 1% precision that's claimed there for the sun. That also requires a heavy metal abundance of 0.0155. And that's where you hit this issue because the current estimates of the heavy metal abundance in the sun are 0.014864. A small difference, but profound. And all of this difference comes from the differences, change in the oxygen abundance. If you plug in that metal abundance into the helioseismology calculations, you have a lower helium abundance, so the age, so the age of the sun actually goes down to 4.41 to 4.55 gigayears. So that's the conflict there. The current helioseismology models can't match the age of the sun with the oxygen abundance that is currently being measured. So, oxygen, how is that measured? It's actually based on measurements of very few lines, and it's mainly forbidden lines, because those you can treat in LTE. You can look at permitted lines, but then you have to take into account non-LTE effects, and basically what you're doing is you're taking a model for the sun, you're taking the velocity structure of the sun's atmosphere, you're taking the abundance of elements, and you're predicting a line profile, and then you're matching that against observations. And the complication is that for all of these forbidden lines, they're all blended with some other elements. And this is just an example here. The oxygen 1 line at 6,300 angstroms is also blended with a nickel 1 line. So you need to account for that blend to derive the oxygen abundance. And I think the main reason why the oxygen abundance changed was that there were better GF values determined for the nickel, for the contaminant lines. You can also use OH lines, but again, that's a more difficult measurement. But so the oxygen measurement within the sun depends on actually a relatively few set of lines. But there is this tension there that actually needs to get resolved. On the whole, the sun is pretty average. I showed this before. This is the abundance distribution of stars in the solar neighborhood, 2 different measurements. They both sampling about 300, 400 solar type stars, FGK stars. The mode of the distribution is at solar abundance. So the sun's pretty average. And again, this is the plot that I've shown several times already, that if you take the old measurement of oxygen in the sun, you find that you're more metal rich than the present day ISM. If you take the new measurement, you're actually consistent with the present day ISM. But of course, the point is that you should actually be comparing against the ISM 4.5 billion years ago. And I don't actually think I've seen anybody do that. But one might assume that 4.5 billion years ago, this whole line slipped down here. So maybe the sun actually, regardless of what the oxygen value is, it's probably metal rich compared to the average ISM value at the time it formed, the average ISM value in the solar neighborhood at the time it formed. And then this is the age metallicity relation I showed yesterday, where the sun has solar abundance, and solar abundance at 5 billion years sits squarely within the distribution of stars. So the sun doesn't appear to be unusual when compared to its compatriots round about it. Okay, so this, Kathy touched on this yesterday. When you look at the meteoritic material, you find there are some nuclei in there that are descended from short-lived products of supernovae. Aluminium-26 decays to magnesium-26, iron-60 decays to nickel-60, and manganese-53 decays to chromium-53. They have relatively short half-lives, 0.7 to 4 million years. So the detection, or the discovery of those nucleotides suggests that the material that the meteorites formed from had been contaminated by material from a type 2 supernova explosion. And there's a number of mechanisms discussed for getting those products into the solar nebula. I meant to check whether most of these mechanisms talk about introducing the material when you have the disk there. I don't know whether anybody has discussed whether you could bring it in before you've actually collapsed into a disk. I should have checked that.
Can I ask you something, actually? Because I want to share it with both in
Yes.
It's just that what I don't understand is why couldn't those unstable things have decayed in the ISM, and then these water products sat around in the ISM as long as they liked, and then get assembled in the meteorite? I mean, I think that can't be right, or else people wouldn't keep on talking about this time constraint of
Right.
a million years. But I don't see why
It's the magnesium, so it's ratioed with magnesium 26 to 24. And you've got to preserve that unusual ratio. And the only way to do that is to keep the aluminum 26 close to that reference element of magnesium, so that when it decays, you get a weird ratio of 24 to 26. That's the one that's time dependent. So what you're measuring are the ratios of 26 to 24. Right?
Yes, I think that's right.
And they've got to be co-located so that you can clock that.
Ah, okay. Yes.
Otherwise, it would just all be a big mess and you'd never notice.
Thank you, Michael. You read the paper better than we did. But the basic, if you accept this, then the requirement is that we must have been near enough to a massive star in the early stages of the sun's lifetime. Kathy talked about this yesterday as well, that the solar system is somewhat unusual in that it has circular orbits for everything. There are many, so this is a plot of eccentricity here against period for exoplanets. And there's the short period objects tend to be in circular orbits, but that's because they've been circularized. But as you go far out, most other planetary systems have highly elliptical orbits. We don't. That shouldn't lead you to think that we're in a nice stable system. One of the things that I think has changed in planetary work is that we've realized how dynamic systems are. We see a lot of the explanations for having hot Jupiters have to do with migration within disks. The Neill model, that's the sort of the best or the most cited model for how the solar system evolved, shows that radical things happen within our solar system too. This is a plot of time in a million years and I think this is, what is this? I think this may be Jupiter and Saturn and possibly Mars. I forget which ones they are exactly. But the main point is that you can have things going along in a nice stable fashion, then things start to go wrong with Jupiter, and suddenly everything switches places. So if you take a model of the solar system and you integrate it back in time, you will see that even although we have circular orbits, I guess it's the same kind of mechanism that's giving you the orbital migration within the galaxy, that you're changing the angular momentum of a particle without actually changing its eccentricity. So this model does say at one point Jupiter and Saturn had switched places. So Bob was saying that think about clusters, everything is moving. Think about the solar system, everything is moving too. It's a lot more dynamical than I think we had ever thought. But the fact is that since they're on circular orbits, the chances are that the sun has not been subjected to an external perturbation, because the external perturbations, because they're asymmetric, will lead to eccentricity. So as Kathy was saying yesterday, that gives you some kind of constraint in the environment. Neptune's the last major planet. There's a nice HST picture of Neptune. I always wondered why they were so excited when they saw a storm on Neptune. There's a storm on Neptune. Wow. The main reason is because Neptune's 30 AU out, so that means it gets 900 times less flux than we do. So actually setting up a storm on Neptune is quite difficult because there's not much energy, but that's beside the point. 30 AU, the last major planet, that could set some kind of bound to the dense part of the protoplanetary disk. Then there's the Kuiper Edgeworth belt beyond that, going out to 50 AU, where you've got low mass icy objects. The total mass in this system is only 1% or 10% the mass of the Earth. And the largest members are comparable to Pluto in size. But that outer edge here may represent some other limit set by external perturbations when the solar system formed. The Oort Cloud. So that's we don't really understand a lot about the Oort Cloud. We know that there's a large reservoir of cometary material at very large distances from the sun, 2,000 AU out to 60,000 AU. Oort originally identified this based on the fact that there were all these near parabolic comets coming in to the sun that seemed to be coming from a spherical distribution at large distances. That's a very easily perturbed system. However, this doesn't actually tell us anything about formation, because if you look at the models for forming the Oort cloud, what you do is you take material that was formed probably within the Kuiper belt, perhaps even into Jupiter, and you kick it out there. So the models for forming the Oort cloud actually have the highest rate of population is 800 million years after the sun formed. So this is a structure that formed presumably well after the sun had moved away from its natal environment. So yeah, it tells us nothing about, it tells us a lot about how much the sun has been perturbed since then, but not a great deal about its formation. And then Kathy mentions, sorry?
Is there evidence for similar structures on other stars?
I don't believe there's hypotheses. I don't believe that there's any direct measurements because it's such a low density that it's.
But is it conceivable to be observed, or is it impossible?
I'm not sure I could think of a way to observe it. I mean, even our own Oort clouds, we don't really have a good handle on its density because all you do is count comets coming in and get some notion there. And there are no direct observations, of course. Okay, so Sedna. This is Mike Brown and Chad Trujillo and Rabinowitz found this in 2003. Mike Brown's Twitter handle, I think, is Pluto Killer. This is one of the reasons why Pluto got demoted to dwarf planet, because they found Quaoar, Sedna, a couple of others that are basically almost the same size as Pluto and out there. So you either had to have 15 planets in the solar system or decide, well, Pluto is just one of the largest objects that's out there within the Kuiper belt. Sedna's interesting because it's so far away. It was discovered almost 90 AU away when it was discovered. It's very red, probably a tholin-coated surface, diameter 1,200 to 1,600 kilometers, so a bit smaller than Pluto, but not by much. Actually, I guess it could even be bigger than Pluto, depending on the albedo. And the mass, they estimate, is only about 1/10 that of Pluto, although that, I think, is just a total guess. Yep?
A question regarding the Oort cloud, perhaps it's, I don't know. If you said that this are probably objects that were ejected from the Kuiper belt, but is it very easy to produce a spherically isotropic distribution via these kind of ejection?
I can't say for sure, but I believe it must be, since I don't know the details. But it actually wouldn't just be. It'd actually probably be mainly Jupiter. It's probably taking debris that's closer in and ejecting it out there. But I don't know the definite answer to that. But I'll look that up. Yes.
Naive question: is it possible that these dwarf trans-Neptunian objects were once moons of more massive planets in the solar system and were ejected by some encounter?
I don't think so, because we're finding too many of them. I think you would So this is not based on, and also you'd have to account for why they were all ejected out to sort of large distances. But some of them could. I mean, some of them could be. But yeah.
I mean, it's rather the other way around. I mean, most of the moons around Saturn and the larger bodies are actually acquired quite recently. So,
Yeah. Sorry.
most of the moons have not formed as moons.
Yeah, so Sedna is on this remarkable orbit so this is moving out in the solar system. There's the asteroid belt. There's Pluto. Sedna's orbit is shown here with the Oort cloud out here. It's essentially going from a perihelion around about, 76 AU out to almost 1,000 AU. And so the argument is that one method of getting an object onto this orbit is to take something out of the Kuiper belt with by a perturbation from a star within 400 to 800 AU of the Earth, of the Sun, and this would have to happen, well after the formation of the solar system. So what does all this tell us about where the sun formed? Well, we don't know whether they formed in clusters, but we know that most stars formed in clustered environments. The fact that you've got products from a supernova indicates that the sun must have formed in an environment that was capable of producing a fairly massive star. And then the radio cutoffs indicate that there was some mild dynamical interaction. I can't remember if I put it up there, but Kathy yesterday said that 200 to 300 AU is the closest, really, that you can have an interaction without introducing significant ellipticity in the orbits. So can you quantify this further? So in the paper, Fred Adams goes through and discusses, in the review, Fred Adams talks about the mass of the sun. I'm actually not sure this is relevant to anything. I mean, the mass of the sun is what it is, and I don't think it actually affects anything that went on round about it. The fact is the sun, there's 15% of the systems within the local 8 parsec sample that have a component that is or was more massive than the sun, because there's 12 white dwarfs, all of which were more massive than the sun when they weren't white dwarfs. So, you know, it's high mass, but it's not super high mass. 30% of G dwarfs are single. So, you know, the sun's a single star, but that doesn't really tell you anything much else, I think, in terms of where it forms. Contaminating the disk. There have been suggestions. One of the suggestions that was in the literature was that you could actually, well, there is the problem that you need to be close to the supernova, but not too close. There was a suggestion that you could, maybe if you had several supernovae going off, you could mitigate that problem. The problem there, of course, is that having several supernovae go off within an OB association or whatever without disrupting it seems to be stretching things. Actually, so that is an interesting hypothesis, but I don't think it actually flies very well. For the progenitor mass, yeah, no, I thought it was something. For the progenitor mass, Fred Adams looks at, the arguments are that in order to get sufficient material into the system and the yield for the various elements that are observed, you actually need something like a 25 solar mass object to go supernova. And Williams and Gaidos set an upper limit of 75 solar masses for this, the parent star for the supernova. You can run through an argument based on cluster size to try and figure out how big a cluster needs to be. So this is just a probability argument based on taking a standard mass function and saying, I want to form at least one 25 solar mass or 75 solar mass or 50 solar mass stars. How many objects do I need in order to have a reasonable probability? And if you want to form something with 25 and 50 solar masses, and so you're assuming here that everything is the same mass function, that there's nothing crazy going on there. Somewhere between 1,000 and 2,000 stars are what you need in the cluster in order to have a reasonable chance of forming the supernova. So you're talking about a fair-sized cluster then. It's probably, it's close to Orion. The other thing to factor in is in terms of the pollution, is that the supernova has to go off while there's still gas within the disk around the sun, the protoplanetary disk. There's no point in the supernova going off after the meteorites have formed. So that sets a time limit of maybe 10 million years between the sun's forming and the supernova going off. If you say that the supernova progenitor had to form at the same time, you actually say that it's difficult for a supernova for a star less massive than 20 solar masses to do the pollution, because the lifetime to supernova is round about 10, 11 mega years there. A more massive star, a 25 solar mass star, is generally expected to hit supernova in about 6 to 7 million years. So I guess it's 7.5 million years to core collapse. So more massive. I think this is one of the main indications for saying why you want to go for 25 solar masses. Of course, you don't actually have to have the sun and the supernova forming at the same time. And then, so distances. So this diagram here is the distance to the supernova and the size, the distance within the protoplanetary disk where bad things happen. There are two bad things that can happen to the disk. You can get ram pressure from the supernova, that if the ram pressure from the supernova exceeds the gravitational binding energy, you're going to strip the disk. The other thing is that the momentum transfer from the blast wave can just have the same effect. So essentially this is saying that if a supernova went off at 0.01 parsecs, the residual disk around the sun would be less than about 3 AU. So we can say the supernova did not go off that close. If you want to get out to disks that are about 100 that survive to about 100 AU, 90 to 100 AU, then this is where the 0.1 to 0.3 distance limit for the supernova going off comes in. So, yeah, and there's a paper by Chevalier that suggests that any supernova that went off within 0.2 parsecs of the sun would do really bad things. But then you have to capture the material, so you can't have it too far away. And I guess Kathy mentioned this yesterday, and less than 0.3 parsecs seems to be a reasonable distance for a 25 solar mass supernova. Higher mass you can put further away, but you're still talking about something that went off within probably less than half a parsec of the sun. So it's a kind of Goldilocks situation. You want to collect the materials, but you don't want to collect too much of them, because bad things come with them. So this is just saying that the mean stellar density within populations is 100 parsecs, and this is to say, wake up. So the edge of the disk. Typically, if you're looking at to produce an edge in a disk, you typically need an encounter that's roughly 3 times further away than the edge you see. So in the disk, we can see two kind of cutoffs, 30 AU, 50 AU. You take this factor of 3 to do it for the encounter, and you have that means the encounter is somewhere between 90 and 150 AU. So this has to have happened during the gas-rich phase. This is before you form planets, so you're cutting down the size of the disk. You're truncating the disk, but you're not actually doing anything to the orbits of the planets because they haven't formed yet. So this is very early on in the sun's life. And basically this is saying that within a typical cluster, with the typical density of 100 stars per cubic parsec, velocity dispersion of 1 kilometer per second, then typical encounters look like they're about a few hundred AU. So the typical encounter within a cluster of this size is actually going to be somewhat larger than this. So maybe either the sun happened to be in this average cluster, and it just was unlucky and it happened to have a close encounter, or maybe the sun was actually in a higher density environment than your typical embedded cluster. Yep?
Question. I think I missed this earlier on. I understand why the disk has to have an edge, but why does it have to be truncated? I mean, couldn't it have been limited by the original infall angle of mass, for example?
I think that the sizes of disks that we see are larger. And I mean,
It doesn't stay sharp.
yeah, okay.
It's the sharpness. Because the sizes you're quoting are fairly typical for pre-main sequence disks, but the sharpness.
Yeah, they actually have to have a pericenter within a certain distance to get it sharp.
Although the sharpness is inferred from the fact that you don't have a large planet outside Neptune. So it may not actually be as sharp as that. I mean, going through this, I was trying to remember exactly what my rationale was for writing it, but but you know, it's certainly, this is a fairly close encounter that you're talking about here, with 90 to 150 AU. So it does imply a fairly high star density, and it's also true that we don't really. I mean, just because a giant planet didn't form outside the orbit of Neptune, doesn't necessarily mean that the disk ended right at Neptune. So this may actually be more a fantasy calculation than anything else. So ignore that. But this is more solid, and this is what Kathy talked about yesterday. Basically, these are curves of So disrupting the solar system through interactions and the eccentricity of the planets would end up on based on interactions within, what is this, 200, 400, or 600 AU, I think it is from here. But again, as Kathy said yesterday, you don't want to have something happen within 200 to 225 AU. Let me just skip that. Evaporating disks, we talked about that yesterday as well. Evaporation isn't really a problem unless you're sitting next to an OB star for a significant time. You can survive the far UV radiation for a reasonable, so you have to be in the outer part of a cluster, but unless you're orbiting in a very close proximity to the trapezium stars, you're not actually going to be affected too much. And these are the lifetimes then for the gas phase. So what is this? Right, yes. You need to be, basically this is saying you need to be extremely close. This is for EUV and this is for far UV radiation. And essentially this is the size, the truncation of the disk depending on whether on the UV flux. So at 10 to the 15s photons per centimeter, you're going to get this kind of, and this is then the time of exposure. So 10 to the 15 gives you, at 60 megayears and 10 to the 15 photons is going to give you a very small disk. 10 to the 11 photons, you're talking about truncations that are not going to have a major impact on the size of the residual galactic disk. Not the galactic disk, the protostellar disk. Okay. So one of the interesting things about Sedna, it needs to have a perturbation, as I say, after the sun has left its native environment largely. It needs 400 to AU encounter. The gas disk is gone. It could occur within the parent cluster. It could occur within after the cluster has dissipated. Stellar encounters aren't very frequent, and so far we haven't found any other analogues to Sedna. There's an interesting paper by Kai, Brosker, and Quinn who argue that maybe the way to produce Sedna is to have an encounter when the sun is migrating. They argue that the sun could have migrated over something like anywhere from 5 to 10 kiloparsecs. If you have the sun migrate, you can bring it through higher density regions and increase the chance of having this wide encounter that creates Sedna. So it's an interesting paper. Yep.
Could this 400 to 800 AU encounter also account for maybe for the ejection from the cluster we found here?
I don't know. So I would turn to Bob on that. A 400 to 800 AU encounter, could that eject the star from a cluster? It seems to me distant. Yeah.
I doubt it. I don't think you have enough energy at that. And basically what you want to ask yourself is what is the orbital velocity at 800 AU compared to the internal velocity of the cluster?
I think actually the other thing is that if you're going to give enough energy to eject the sun from a cluster, you would think you would do something bad to the planetary system as well.
So it's likely to just diffuse? Or
Yes.
dissolve?
I think that's the hypothesis, yes.
Mm-hmm.
I think any kind of high energy interaction like that would have done something bad to the planetary system.
Neill,
Yes?
the suggestion is that you might have had the Sedna encounter while it was in the field, it was just a different field.
Yes.
Yeah.
Now you,
I haven't looked at the numbers, but of course the velocity dispersion field is larger than in your birth aggregate,
Right.
as well as the density being lower. So
and the other thing is that if you can migrate, then you can migrate through different densities. So you've got a larger range of environments to take the sun through to increase the probability.
as I say, for gravitational focusing, you've got that problem that you've got a higher velocity dispersion. I'm sure they put the numbers into it.
Yeah. I mean, it's also kind of, we have a neat mechanism and let's see what we can do with it. But,
Maybe,
yes?
maybe I'm wrong, but I remember that the Oort Cloud extends to 500 astronomical units.
Which,
The Oort Cloud. Or Oort.
no, the Oort, yes. No, well, yes, so, but the
So
thing,
if you have an encounter at 800 AU, we are going to disrupt the hot cloud.
You'll disrupt it, yeah, you may not disrupt it entirely. And the other thing is that you could have the encounter before you form the Oort Cloud.
But after forming Sedna?
Yes, because remember, I mean, it's essentially you're forming Sedna and all the Oort Cloud material in the interior solar system and then putting it out there. So Sedna would have been formed, and the Kuiper belt would have been formed roughly at the same time. So you have this reservoir of material then in the inner solar system, and that's what you use to populate the Oort Cloud. But I also think that a stellar encounter, you wouldn't necessarily destroy the Oort Cloud. It would probably be bad for Earth. You'd probably have a bombardment phase. Maybe this was the heavy early bombardment, tying things together. Anyway, this is putting all these pieces together. This is what Fred Adams came up with as the most likely size of the parent cluster for the Sun. A few thousand stars, both to account for having a high mass supernova, but not destroying the Earth cluster. So as I said, there have been searches. There have been searches to try and find siblings of the Sun, stars that are essentially identical in every respect, metallicity, age, and so on to the Sun. Simon Portuguese-Zwart has argued that this is something that we could do. He took a dynamical simulation and he looked at the kind of drift of stars away from the parent cluster and came up with a number of candidates, relatively bright stars, G-type stars, that have been suggested as potentially identical to the Sun. And then others, Brown and Portuguese-Zwart and Bean, looked through the Hipparcos catalogue to come up with a number of candidates. There's remarkably few candidates that people come up with, a half dozen at most, and Bobilev et al. Carried out the same exercise. And just to run through, so you're looking for something that's about 4.6 billion years old. You want it to be solar metallicity. You want it to have a velocity which is consistent with when you trace back the orbit that the Sun and this object could be in the same place at the same time 4.5 billion years ago. None of them, these are 4 of the candidates here. HD 28676, it's an F5 dwarf. It's the right metal, it's within 0.04 of solar metallicity. But the problem is that the radial velocity the space motion doesn't fit. You can't actually get the orbits to match. HD 83423, well, it turns out to be metal poor relative to the Sun. HD 175740 is, again, slightly metal poor. It's a binary system. HR 6669, it's very metal rich. So none of these candidates actually stand up to close scrutiny. We're getting there. Those are not my dogs, but this is how you all feel. Yes?
The basic arguments you put forward on the metallicity.
Yes. Well, the metallicity.
Is this quantity well determined?
It's determined typically it's probably determined to an accuracy of 5%. So I think for these two, the offset is real.
0.1 dex is not so much.
Yes. But I think in this case, this is based on high resolution spectra analysis. So I think it's actually fairly solid.
Okay, besides you have to see how it was at the beginning of the solar system, because you have a change of 10% of the metallicity due to atomic diffusion inside the star.
So yeah, well, I mean, and the other thing is there could actually be some slight range of metallicity within the system itself. However, none of them quite stand up. I think the other side is tracing back the velocities. They don't quite match up. But it's an interesting exercise. The other interesting thing is that there have been suggestions that maybe the Sun formed an M67, which is about the same age as the Sun, and it's within 0.04 dex of solar. So the paper by Pichardo et al., they model the orbits of the Sun and M67. And I guess the other uncertainty here, of course, is that you're modeling the orbit and taking it back, and there are potential for perturbations in there that could change the orbit. But if you just take the orbits that we have at the moment, then this, I think, is the closest. Taking it back to 4.5 billion years, the Sun would be down here, and M67 would be up there. So there isn't a close encounter between the sun, or the closest, when the sun and M67 are close together, the relative velocity is 20 kilometers per second different. So based on this, there's a very small probability that the sun originated in M67.
Is there a supernova remnant in M67?
I don't believe there is. And it would have gone by now, actually. I mean, actually, if there was a supernova in the parent cluster, then if you had any kind of reflex velocity, the neutron star would be long gone. So. But the other thing is that should you actually ever expect to see siblings, the Portuguese Oort model was fairly simple. It didn't take into account density waves and spiral arms. And there's a nice paper by Mashurov and Acharova. And they basically find it much less likely that anything from the sun's natal cluster would be near us now. This is the dispersion of points for a couple of models of where the sun's clusters would be, and this circle here is 100 parsecs. So you say if the sun's parent cluster included 1,000 stars, none are likely to be within 100 parsecs. If the sun's parent cluster had 10,000 stars, then, to quote the paper, the task becomes less hopeless, which is not an exhortation to go out and do it.
Sounds like a PhD thesis topic there.
I wouldn't give it to a student. You might. So, as I said, the original input then, so what about solar migration? Migration clearly occurs. We've gone over this, the oxygen abundance, many times. I think Gaia here is going to be extremely interesting in providing much more detailed kinematic information so we can look at the kinematic structure of local, not just local, but on a larger scale, all stars, and actually try and figure out what fraction of the disk undergoes these kind of radial motions, what stars are being caught up. But even with Gaia, trying to get a full understanding of what happened in the past. I think there are all these encounters where you lose information on what was going on in the past. So I think my feeling is that we have, from the supernova evidence, we have an indication that the sun formed in a fairly clustered environment. I think going beyond that is going to be extremely difficult.
Can I ask you a question about radial migration? Is it the idea that some stars do it and the sun might have done it, or that it might have been a large-scale effect sculpting the formation of the disk, and you could apply it to things like the G-dwarf problem and all the things that you used to do with it?
I think it's more the former, I think, than the latter. That you don't. It's not like everything is shifting back and forward. But I don't think we have a good handle yet on what fraction of the disk might be affected by these kind of motions, and when they would be affected. So quantifying that side of things is going to be important. Yep.
There is a paper of Whelan from '96 where he is doing this argument with radial migration.
Right.
And he traces back that the probability of the sun is most likely that it formed somewhere between 5 and 6 kiloparsec.
Yeah, I think that's tied in, I think, largely to the abundance distribution. And I think that was one of the prime pushes for looking at the migration factor. But my feeling is that I don't think we necessarily understand the abundance spread at a given location well enough to be that equivocal, or that unequivocal. So I would be more equivocal. But yeah, certainly Whelan's paper was important, and it was the first one that kind of brought that in, that this was something we needed to look at. Let me just skip that, because this is okay. I think actually one thing that we really need to try and understand is how frequent planetary systems like the solar system are. This is Kepler's. It's actually a year old now, so it's way out of date. But this is, these are all orbital period versus, what is that? Mass, I believe, whatever, for Kepler objects. And it's now, Kepler has really thoroughly populated the plane. We need to understand how often habitable, stable systems like our own form. Kepler's shown that forming planets is really easy. Forming habitable systems may be more difficult. And forming habitable systems that are in zero eccentricity orbits may be even more difficult still. I think if we can start to get statistics on that, then we may start to get a different insight into how likely it was that the sun formed or where it might have formed. Because if it turns out that almost all planetary systems have extremely eccentric orbits, then we're really looking for a fairly unusual place that the sun formed. If it turns out that solar system-like planetary systems are fairly common, then maybe there's a wider parameter space range. And it may just all come down to the fact that we were really lucky.
Can I comment on that?
Yep.
Just that the radial velocity results currently certainly say that a lot of planets are, planetary systems are much more eccentric
Mm-hmm.
than the sun. But that's not related to its external environment. That's almost certainly planet-planet scattering that's produced
Right.
there. And we see that in order to leave our solar system alone, we're okay as long as nothing comes within 200 AU of you. And most Earth environments, stuff doesn't come within 200 AU of you. So I think the story about whether it's eccentric or not is probably not related to environment. It's something about formation history.
So it's more looking at whether you form several massive objects in the wrong place.
Those scattering events that other systems do.
Yes?
So is it the selection effect that the large part of the sample has such high eccentricities?
Well,
Because, of course, Kepler is sort of biased towards very close-in planetary
I'm
systems.
not
with-
talking about Kepler, I'm talking about the radial velocity.
Okay, yes, sorry.
I think with Kepler, Kepler is still biased towards the smaller period system because it's only been running for a year and a half or 2 years. And I think it will be interesting to see what comes out of there. Certainly for the radial velocity surveys, you're mainly looking at things where migration has happened. So we need to try and get or migration has happened in a bad way to put something really close in. I think just the general statistics as a whole would be interesting. Yeah?
I should comment on your comment. I'm wondering if it could sort of be related to the environment. Only because the scattering is going to happen if you've got more massive planets, which is possibly dependent on the environment it forms. The environment allows it to form massive planets, which will keep it just a lot and get rid of a lot of the stuff before the massive planet. So if you're not directly related, it might
There might be an indirect chain, but I think it's just the fact of the numbers that you have to get into 200 AU to make much difference.
No, I think she's saying you can't get three big fat gas giants in many star-forming regions because the disk evolution properties might be such that...
No, I'm addressing exactly that. I'm saying that to change the disk evolution properties down where you're forming your gas giants, which is at tens of AU, you have to be in a very, very dense environment.
I think it's full of evaporation. That would be the environmental context that would make planet-planet scattering in that environment.
Oh, if we're right next to it, if we're right in the danger zone in the centre of Orion, yeah. But not even for the bulk of the stars in the air and seas that thing. So, I think in principle it's absolutely fine, but just how to get those environmental effects for the bulk of the stars in the cluster right down to those small radii.
Why don't we pick this up in the discussion later? And I will just conclude by saying, yeah, the sun probably formed in a fairly massive star cluster just based on the supernova, but sufficiently sparse not to do bad things. And looking for solar twins seems to require undue optimism. And I'll leave these two questions there, and I will close. Thank you. Coffee.